I welcome you all students to my second session on bonding in complexes. In the earlier session, we tried to understand bonding in the complex ions by applying valence bond theory. In this session, I would explain some aspects of the crystal field theory. According to the crystal field theory, each ligand is considered a point charge. The interaction between the ligand and the metal ion is electrostatic in nature. The d orbitals of the metal ion have same energy and we say they are degenerate orbitals. That means the metal ion is surrounded by a symmetrical energy field around it. As the ligands approach, this degeneracy is disturbed. That means the d orbitals no longer have same energy. Two of the d orbitals have higher energy than the metal ion and three of them have lower energy than the metal ion. That means the d orbitals are split into two sets. One set of two orbitals having higher energy than the other set having three of the d orbitals. I will show you that diagrammatically now. Now you see in the diagram what I explained to you just now. Here you see the 5 orbitals of the metal ion. The 5 d orbitals of the metal ion have same energy. We say they are degenerate in nature. As the ligands approach, the average energy of the d orbitals is raised. This is what we say, the average energy of the d orbitals in the spherical crystal field. Now, as the ligands come closer to donate their lone electron pairs to the metal ion, you see the actual splitting between the d orbitals. Two of the d orbitals, namely the dz square and dx square minus y squared orbitals, are raised and this forms the Eg set of higher energy. The other three d orbitals, namely the dxy, dyz and dzx orbitals, have lower energy than the average energy of the spherical crystal field. This forms the T2G. I suppose you understand. So these are the two sets of d orbitals having difference in energy. This difference in energy is represented by del O, because first I am taking up the octahedral complex. So the energy difference is represented by del O. Later when we deal with the tetrahedral complex, we are going to represent it as del T. I have noted down what I explained to you with the help of the diagram, and you are supposed to learn all these things and write them along with the diagram when you are asked to explain bonding in complexes according to crystal field theory. Now you see the last point that it is noted there is del O is called the splitting energy, and it depends on the nature of the metal ion, its oxidation state and the nature of the ligand. Some ligands cause greater amount of splitting and del O values will be larger, and some ligands cause lesser amount of splitting and their del O values will be less. We consider a metal ion with a D1 configuration. The electron will be in the T2G orbital. This second electron in a D2 configuration will be like this, and the third one will occupy the other d orbital as per Hund's rule. These are the T2G orbitals. Now you have two Eg orbitals. For a metal ion with the fourth electron, that is with D4 configuration, the fourth electron has two options. It could go here to the Eg orbital and stay unpaired, or it could pair up with the electron in the T2G. I will show it like this. The first case will be like this, Eg and T2G. Let us have the second case where the fourth electron pairs up with one of the electrons in the T2j orbital. The first case will occur when this del O, we already saw the difference in energy is called del O, when the del O is less than what is called P or pairing energy. See, to pair up with another electron also, there is some amount of energy needed which is called pairing energy. If the del O or the crystal field splitting energy is less than the pairing energy, it would go and occupy the Eg orbital. The other case where del O is greater than P, that is the energy needed for pairing is less than the energy needed to go to the higher orbital, higher energy orbital, the second case will happen. I suppose it is clear to you. For a metal ion with the D4 configuration, these are the two options for the fourth electron to occupy. As we saw earlier, for certain ligands with respect to certain metal ions, the del O value may be higher. When the del O values are higher, this will be the case, and here you see there are less number of unpaired electrons. So such complexes are called low spin complexes. Low spin complexes, and in this case where del O is less than P and pairing does not take place, you have more number of unpaired electrons, and this refers to high spin complexes. If we arrange the ligands in the increasing order of magnitude of crystal field splitting, you get what you see on the board. This is called the spectrochemical series. It's based on the experimental data obtained from spectroscopic studies. You find the halide ions occurring somewhere on the left side of the series. So, it means that the crystal field splitting is less for the halide ion ligands, whereas for the cyanide and ammonia ligands, the crystal field splitting is greater. Let me explain with the example of the hexafluorocobaltate ion, COF6 3-. The fluoride ion lies to the left of the spectrochemical series, isn't it? Hence, we can say that it is a weak field ligand. For a weak field ligand, del O is less than P. Since pairing energy is higher, it is not favored. Hence, we can assume that the electrons remain unpaired, and we would say it is a high spin complex. And due to the presence of unpaired electrons, it is paramagnetic. Okay. See, if you recall how we discussed bonding in the case of valence bond approach for the same hexafluorocobaltate ion, we took help from the magnetic data. We had the information that it is paramagnetic. When it is paramagnetic, we want unpaired electrons, so we left the electrons unpaired. We took the outer s, p and d orbitals, and we said it is due to sp3 d2 hybridization, it is a outer orbital complex, isn't it so? Now here, with the help of the spectrochemical series, we are able to predict the magnetic behavior of the complex ion. I suppose it is clear to you, and you are able to compare the two approaches to the discussion of the same complex ion. I will give you the example of hexamine cobalt 3 ion. Now, I want you to predict if it would be a high spin complex or a low spin complex, and also you should state whether it is paramagnetic or diamagnetic, taking help from the spectrochemical series. Please pause here and find out the answers, and then come back and listen to my discussion. Now you find ammonia to the right of the spectrochemical series. So it is a strong field ligand. And what about the del O value for a strong field ligand? You can say it is greater than P. Here the pairing energy is lower, hence pairing is favored. Since the electrons are paired, what would be nature of the complex? It will be a low spin complex. And it would also be diamagnetic. Is that clear to you? Very simple. So we have done a very elementary treatment of the crystal field theory. In the diagram, you can see the crystal field splitting for the tetra-coordinated complexes. You see two major differences here. One is the T2G orbitals have higher energy than EG orbitals. Look at that. So these three orbitals dxy, dyz and dzx forming the T2G have higher energy. And the other two forming the EG set have lower energy. And also the magnitude of splitting energy del T is less compared to del O. These are the two things you have to keep in mind when you consider the crystal field splitting in the tetra coordinated complexes. I suppose you have understood clearly the discussion of bonding in complex ions based on crystal field splitting theory. Is that clear?